Amines, Chapter 22. Objectives: 1. Introduction to amines. 2. Nomenclature. 3. Properties of amines. 4. Synthesis of amines. 5. Amine reactions. And 6. Spectroscopy. Your goals. By the end of the chapter, you should be able to name and draw amines, understand the properties of amines, provide synthetic routes to amines, predict amine reaction products, and interpret spectra. 1. Introduction to amines. Amines are derivatives of ammonia, NH3, and they are designated as primary, having one R group, secondary, having two R groups, or tertiary, having three R groups. Natural sources of amines. Naturally occurring amines are called alkaloids. Here are a few examples. Morphine is derived from unripe seeds of the poppy plant. Cocaine is isolated from the leaves of the coca plant. Nicotine is found in tobacco. Some naturally occurring amines are vital to neurochemistry. Adrenaline is the fight or flight hormone. Noradrenaline regulates heart rate and dilates air passages. Dopamine regulates motor skills and emotions. 2. Nomenclature. For IUPAC rules, there are two different ways for naming primary amines. 1. Name the alkyl group ending in YL followed by the suffix amine. Ethylamine, isopropylamine, cyclohexylamine. 2. More complicated primary amines are named as alkanamines. They are named the same way as we name alcohols, but we change the suffix to amine instead of OL. For example, 2R4R, 4,6-dimethyl-2-heptanamine. If the amine is a branch, we use the term amino to name it as a substituent. 4-aminobutanol, para-aminobenzoic acid. If the amine is directly attached to an aromatic ring, the parent name is aniline. We have here, for example, aniline, metachloroaniline, 5-ethyl-2-fluoroaniline. Secondary and tertiary amines. There are also multiple methods for naming secondary and tertiary amines. 1. Name the alkyl groups followed by the amine suffix. Use di and tri if there are more than one of the same group. Ethylmethylpropylamine, diethylamine, trimethylamine. 2. Find the carbon parent chain and use the suffix amine. Smaller groups attached to the amine should be named as alkyl groups with the N locant. For example, S,2,2-dichloro-N-ethyl, N-methyl-3-hexane-amine lets us know that we have R groups that are different on the nitrogen. 3. Properties of amines. The nitrogen atom in typical amines is sp3 hybridized. Let's recall the circumstances under which the nitrogen is sp2 hybridized. That would be when those electrons are going to be contributing to resonance structures. Then they must be in a p orbital. 4, though, are sp3 hybridized N atoms. The bond angles around the nitrogen tend to be around 108. The carbon-nitrogen bond lengths are 147 picometers, which is slightly shorter than C-C bonds, but longer than CO bonds. The trigonal-pyramidal nitrogen atom of an amine carries a partial negative charge on its lone pair. We have a region of high electron density. The lone pair can function as a base or as a nucleophile. When it functions as a base, it abstracts H+. As a nucleophile, it attacks an electrophilic source. Chirality. N atoms with 3 different alkyl groups are chiral. They possess 4 different groups. The lone pair counts as a group. But Amines are generally not optically active, and that's because pyramidal conversion occurs rapidly. It flips. It goes from one configuration to the other. Physical properties. Amines with fewer than 5 carbons are typically soluble in water. Primary and secondary amines can intermolecularly H-bond and have higher boiling points than tertiary amines. Many small molar mass amines have unpleasant odors. They smell like rotting fish. For example, putrescine and cadaverine. Basicity of amines. Amines are stronger bases than alcohols and ethers. Amines can be readily protonated by strong and weak acids. It is useful to have a general idea of the pKa values of protonated amines. In Table 22.1, the pKa values of the ammonium ions are shown of several amines. At physiological pH, that is 7.3, amines exist primarily as ammonium ions. The ammonium ion then predominates. Extraction. In general, amines with more than 5 carbons are only slightly soluble in water. Solubility is enhanced in the presence of aqueous acid. Protonated ammonium ions are cations and therefore water-soluble. Amines can be extracted from organic impurities using an aqueous acid and converting them to corresponding ammonium ions. Alkyl versus aryl amines. The pKa of most alkylamine conjugate acids is between 10 and 11. Aryl amines are less basic than alkylamines. The lone pair is delocalized. The delocalized lone pair is less available for protonation. The presence of electron withdrawing groups also decreases basicity. Amides. The lone pair of an amide is not considered to be basic or nucleophilic. It is extensively delocalized into the carbonyl group. 4. Synthesis of amines. Let's review. Preparing an amine from an alkyl halide. One can prepare an amine by having it undergo an SN2 reaction with something like cyanide, followed by reduction to form the amine. Primary amines can be made from an alkyl halide in this two-step process. The carbon skeleton is also expanded by 1 carbon. Amines can be made by converting a carboxylic acid to an amide and then having the amide undergo reduction with lithium aluminum hydride. That will result in an amine. The carbon skeleton with this set of conditions remains unchanged. Synthesis of anilines. We can prepare these from benzene. First, nitration of a benzene ring would occur, and that would be followed by reduction to provide aniline and aniline derivatives. Synthesis from ammonia. Amines are good nucleophiles and readily undergo SN2 substitution with an alkyl halide. This is an efficient way to make a quaternary ammonium salt. Monoalkylation is difficult because nitrogen becomes a better nucleophile as it picks up alkyl groups. Synthesis from azide. First is the conversion of an alkyl halide to an azide via SN2 by reacting it with N3-. This is followed by reduction to make a primary amine. This is a better way to make a primary amine than trying to monoalkylate ammonia. The mechanism. In the first step, nucleophilic attack and loss of leaving group. The azide ion functions as a nucleophile and attacks the alkyl halide, expelling a halide leaving group. Nucleophilic attack. Lithium aluminum hydride transfers a hydride ion to the alkyl azide. Loss of a leaving group. Nitrogen gas is expelled as a leaving group, giving an amide ion. This is then followed by proton transfer. the amide ion is protonated, affording the amine. Gabriel synthesis. The Gabriel synthesis is used to form primary or secondary amines from phthalimide. First, phthalimide is converted to an anion with potassium hydroxide. Potassium phthalimide is then alkylated via an SN2 reaction. The last step generally employs aqueous acid or hydrazine to liberate the amine. Reductive amination. A ketone or aldehyde is converted into an amine, which is then reduced to the corresponding amine. If the reducing agent is present, the amine can be reduced in situ to form an amine. Reductive amination can be accomplished with a variety of reducing agents and can yield primary, secondary, or tertiary amines. This just depends on if we are using ammonia, we would get a primary amine. A primary amine will give us a secondary amine, or if the reagent is a secondary amine, that would afford a tertiary amine. Sodium cyanoborohydride, which is like sodium borohydride, this is commonly used because it is selective for amines. Since sodium cyanoborohydride does not react with ketones or aldehydes, it can be used in situ during amine formation and yield the desired amine in a one-step synthesis. Here are the strategies to primary amines. There are three options: the Gabriel synthesis, azide synthesis, or reductive amination. 5. Amine reactions. Acylation. Recall that amines are converted to amides with an acyl chloride. 2 moles of the amine are required as one will react with hydrochloric acid. Acylation of an amine can be used as a protecting group. Activating groups. Consider how to perform monobromination of aniline. If aniline is directly brominated, polybromination is observed. The amino group is too powerful of an activating group. Aniline, protected as an amide. The amine must first be protected as an amide. The disadvantage of this synthesis is that amide hydrolysis requires harsh conditions. Aniline and Friedel Crafts. Aromatic amines also cannot undergo Friedel Crafts directly. The amine reacts with the Lewis acid catalyst and deactivates the ring. Ring alkylation. To achieve ring alkylation, then, first the amine must be acylated. Then the ring can be alkylated, followed by removal of the acyl group. Hofmann elimination. Like alcohols, amines can also serve as precursors for the synthesis of alkenes via elimination. It is called Hofmann elimination. For example, in the first step, the amine is reacted with an excess of alkyl halide, followed by the elimination step. Hofmann elimination mechanism. The amine is first converted into a good leaving group. Excess methyl iodide will convert an amine to a quaternary ammonium salt, which serves as a good leaving group. A strong base then causes E2 elimination. Silver oxide is commonly used because it produces hydroxide. Hofmann eliminations give the terminal alkene because it is the Hofmann product and it's regioselective for it. For example, here we have the formation of the good leaving group already in place. The base abstracts H+. As the sigma bond breaks and forms a lone pair, the leaving group leaves, resulting in the Hofmann elimination product. E2 requirements. Sterics in the anti-coplanar conformation hinders attack at the more substituted site. Reactions with nitrous acid. Nitrous acid is unstable and has to be generated in situ to react it with an amine. Nitrous acid loses water to form the active electrophile, a nitrosonium ion. In the first step, in order to get to that point, sodium nitrite is reacted with HX, in this case hydrochloric acid, to give nitrous acid. Nitrous acid undergoes another proton transfer and the loss of water in order to form the nitrosonium ion. The ion itself is extremely electrophilic and very unstable. It immediately reacts with an amine as soon as it forms. Secondary amines and nitrous acid. Reactions with the secondary amine yields an N-nitrosamine. The mechanism. Once the ion has been produced, it undergoes nucleophilic attack by a secondary amine. Then this is followed by a proton transfer, resulting in the ammonium ion being deprotonated. Nitrosamines are potent carcinogens and are found in many food products, including cured meat, fish and beer, and bacon and tobacco smoke, etc. Amines and nitrous acid. Reaction with the primary amine yields a diazonium salt, that is an R group attached to an N triple bonded to another N. This process is called diazotization. The mechanism. In the first step after the nitrosamium ion is produced is nucleophilic attack. A primary amine attacks the nitrosonium ion. This is followed by proton transfer. The resulting ammonium ion is deprotonated. Then another proton transfer. A proton is removed, forming a double bond between the nitrogen atoms. A third proton transfer. The oxygen atom is protonated, forming an excellent leaving group. Loss of a leaving group. Water is expelled as a leaving group, generating the ion. Reactions of aryl diazonium salts. These are extremely unstable and decompose to form a variety of products if they don't explode first. Aryl diazonium salts are a bit more stable and are synthetically versatile. Sandmeyer and Scheiman. These reactions have aryl diazonium ions reacting with copper salt to install a halogen or cyano group onto the ring. The Scheiman reaction is the fluorination of an aryl diazonium ion. A hydroxy group may also be added. Installing a carboxy group. Overall, the Sandmeyer reaction is part of a multi-step sequence of installing a COOH onto a benzene ring. These are the different steps. The first four will result in the N2+ species being added. Then this is followed by the addition of copper cyanide, followed by acidification and heat to get the COOH. Activating effects. The diazonium ion can be replaced with a hydrogen atom. This is useful when the amino group is needed on the ring temporarily to take advantage of its activating or directing effects, like we see here. It can then be easily removed in order to give the target compound. Azo coupling. Diazonium salts also serve as electrophiles and are attacked by activated aromatic rings via electrophilic aromatic substitution. This process is called azo coupling. Azo dyes. Azo coupling is also used to produce azo dyes, like shown here. These azo compounds are highly conjugated and have brilliant color. Varying the substitution on the rings affects the specific dye color. Nitrogen heterocycles. These are cyclic compounds that contain atoms of more than one element. Pyrrole and imidazole. Pyrrole is a simple aromatic heterocycle and undergoes electrophilic aromatic substitution, even faster than benzene. Substitution at carbon number 2 gives a most stable intermediate. Imidazole is also an aromatic heterocycle and is found in naturally occurring compounds. Pyridine and pyrimidine. Pyridine is a 6-membered heterocycle. The lone pair on the nitrogen is not delocalized and therefore it is a weak base. Pyrimidine is like pyridine and is a common moiety of base in biological molecules, for example, in DNA base pairs. Pyrimidine and pyrimidine can undergo EAS reactions, however, usually with low yields. Pyridine can undergo bromination at 300 degrees Celsius, for example. Review of reactions. Preparation of amines from alkyl halides, carboxylic acids, benzene. Azide synthesis and the Gabriel synthesis. Reactions to prepare amines. Amines can be prepared via reduction using ammonia, a primary amine, or a secondary amine. Each one will in turn convert ammonia, for example, to a primary amine to a secondary amine, and a secondary amine to a tertiary amine. Reactions of amines, key reactions: acylation, reactions with nitrous acid, Hofmann elimination, reactions of aryl diazonium salts. The key reactions: Sandmeyer reactions, fluorination, which is a Scheimann reaction, other reactions of aryl diazonium salts. Azocoupling. Reactions of N-heterocycles. The key reactions is that they undergo EAS, but usually with low yields. 6. Spectroscopy, IR. Amines will generally give broad IR peaks between 3300 and 3500 wave numbers that are less intense than OH stretching. Recall that primary amines will give two NH stretch signals, symmetric and asymmetric stretching. Secondary amines will only give one NH stretch signal, while tertiary amines do not give one because they do not have any NHs. Proton NMR and carbon-13 NMR. The NH proton generally appears anywhere between 0.5 and 5 parts per million in the 1H NMR. Solvent concentration and temperature can affect the chemical shift. Because NH protons are generally exchanged at a faster rate than the NMR timescale, NH protons generally give broad signals with no splitting. If a deuterated solvent is used, NH proton peaks oftentimes just completely disappear. Protons adjacent to the N atom typically show up around 2 to 3 parts per million. Carbon atoms bonded to the nitrogen will typically come at about 30 to 50 ppm. Mass spectroscopy. Compounds with an odd number of nitrogen atoms have an odd mass molecular ion in the mass spec. Amines also typically undergo alpha cleavage in the mass spec, giving predictable mass fragments.